One of the important topics we need to talk about is the cardiac cycle. Of course, the cardiac cycle is all the events that occur during one heartbeat. And we divide the cardiac cycle into systole and diastole. Systole basically means contraction. Diastole means relaxation. Now remember, depolarization leads to contraction. Repolarization leads to relaxation. All right, so again, we have two different things going on here. We've got what's going on with the atria. So we have atrial systole shown here, followed by atrial diastole shown here, 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 and here. So we have atria going through contraction only in one picture, and the rest of atria, we can see here in our graph, the rest of the atria are going through a relaxation period. All right, now notice then we have ventricular systole starting here and ventricular systole continuing here, and then I have both atrial and ventricular diastole in these pictures. Again, systole is contraction, so the red in the picture is not blood flow, the red in the picture is contraction. The black arrows are blood flow. Okay, so a couple of things that we want to see. So if we go to our starting point, atrial systole lasts about 100 milliseconds. So that contraction is going on for about 100 milliseconds. Now that contraction is actually squeezing about the last 30% of the blood that's going to be squeezed down to the ventricles from the atria. That contraction is going to squeeze that. The first 70% of blood that went through there just filled the ventricles up passively. So in this picture, when blood's coming through the superior and inferior vena cava and back from the pulmonary veins to the left side, all the blood going from the atria to the ventricles is passively just flowing through the open valves, the AV valves. There's our tricuspid and there's our mitral valve. So 70% of the blood is just flowing into the atria, down through the open valve into the ventricles. But that last 30%, we have to squeeze it into the ventricles. Now, notice that my atrial systole does not overlap with ventricular systole. Atrial systole squeezes and stops before ventricular systole starts squeezing. And again, that 100 millisecond delay that we actually had at the AV node allows this contraction and the squeezing of blood to occur before we start squeezing blood out of the ventricles. Because a real important concept you really need to get is that the opening and closing of valves is done by the pressure of the blood. Those valves do not open or close according to the electrical signal. They open or close according to the pushing of the blood against them. So notice here in this picture, my valve is closed, but when blood builds up in here, it pushes it open. Okay, now to squeeze that last 30%, then I squeeze the blood through here. But when my ventricular systole begins, after my atrial systole ends and my atrial diastole begins, then now the squeezing of the blood here actually pushes this once open valve, pushes it closed. Notice this valve's open here, but when this starts squeezing the blood up, it closes that valve. Now, notice I have two ventricular systole phases, phase 1 and phase 2, or first and second phase. And in phase 1, we're simply starting to squeeze the blood out. So the first thing we've got to do is close that valve so the blood doesn't come back where it came from. But phase 2, or the second phase, means when we continue to squeeze, we now open up our semilunar valves. Notice that semilunar valve is closed here, it's closed here. But as I squeeze the blood, the pressure of the blood opens up those semilunar valves, and now I can actually eject blood from the ventricles, either into the aorta or into the pulmonary trunk. Okay, now, after we squeeze the blood, after ventricular systole is over with, then ventricular diastole or relaxation can occur. So a real important point is, I cannot have atrial systole at the same time as ventricular systole, but what I can do, I can have atrial diastole at the same time as ventricular diastole. So I can't contract them both at the same time, but I can relax them both at the same time. Now notice in this picture, when our ventricles have relaxed, whatever blood, because not every drop of blood gets squeezed out. Okay, so whatever blood does not get squeezed out falls back down to the bottom of the ventricles. In the meantime, blood is coming into the atrium through the pulmonary veins and through the inferior vena cava and superior vena cava. Now, as blood starts filling these back up, the pressure of that blood opens these valves. So that's why we can distinguish between this stage, ventricular diastole, and this stage, ventricular diastole. I have early and late. Now, what do we see the difference in the picture? Well, here, all my valves are closed. Notice my AV valves are closed because I closed them here. Notice that my semilunar valves are closed because as soon as we started relaxing and blood fell back down, the blood that got past here in the aorta and here in the pulmonary trunk actually came back from the other side and closed the valves from the other side. So notice that in this picture, all my valves are closed, and in this picture, all my valves are closed. Now, we actually have a term for that. We call it isovolumetric. Here we would call this isovolumetric contraction, and here we would call this isovolumetric relaxation. So I'm isolating the volume of fluid due to all my valves being closed. Here they're all closed due to the contraction. Here they're closed due to relaxation, blood pushing them closed from the backside. So my second or late phase of ventricular diastole is when the blood that's filling out my atria overcomes the pressure of the closing of the valves and reopens them, and then I can start all over. And notice all this occurs in about 800 milliseconds. Okay, so again, even when we were talking about our timing back here, we said the whole time for the signal to travel from here all the way down and across was 225 milliseconds, because we know that in reality, the contraction actually only has that 370 milliseconds, and actually the ventricular contraction, it was only 270 milliseconds. But the contraction of this and this both, starting here and ending up there, was only 370. So the rest of the time is the combination of the relaxation. You'll definitely need to be familiar with this picture and what's happening in these phases, as far as, which one's the, atrial systole, which one's the first phase of ventricular systole, second phase of ventricular systole, what's actually happening in this, and then our isovolumetric contraction and our isovolumetric relaxation, which one is that? So you need to definitely be familiar with this picture. You can ask questions if you're not sure. Okay, the next major concept is cardiac output, which by definition is the amount of blood pumped out of each ventricle in 1 minute. So again, we have a time, which is 1 minute. And so when we take our heart rate, we say how many beats in 1 minute, and we have a volume, the amount. So our cardiac output by formula is heart rate, beats per minute, times stroke volume. And stroke volume is literally how much gets pumped out, and especially we talk about what's getting pumped into the aorta from the left ventricle, how much per beat. Okay, now heart rate can be affected by our autonomic nervous system. In other words, our fight or flight or arrest and digest. Fight or flight is going to cause our heart rate to go up. And of course that's our sympathetic nervous system. And then our parasympathetic nervous system, the vagus nerve, is going to kind of keep a brake on the heart, so it's going to slow the heart rate down. And then of course hormones can also affect heart rate. We know that epinephrine would speed the heart up, acetylcholine would slow the heart down. So those hormones can definitely have an effect on the heart rate. All right, now stroke volume then is actually defined by end diastolic volume and end systolic volume. So let's look at what we mean by that. So looking at this and comparing what's going on in the heart to what's going on in a pump. So notice that when blood is entering into the ventricles, it's like water or whatever fluid entering into the pump. At the end of the relaxation cycle, and once we have actually squeezed that last 30% of blood into the pump, before we start squeezing it out of the ventricles, then we have our end diastolic volume. So notice here, our end diastolic volume, the most amount of blood we can get in the ventricles, we're going to subtract the amount of blood left over once we have squeezed it out. That's our end systolic volume, and that will give us our stroke volume. So again, looking at this, notice if I've got this amount, which is how much I could get into my ventricles, and then whatever I've squeezed out is my stroke volume. So how did I figure it out? Well, if I know my end systolic volume, my ESV, I can subtract this amount from that amount, and that will give me how much actually got squeezed out. So my end systolic volume is the amount left in my heart after I contracted what didn't actually get squeezed out, what was left over. So I subtract what was left over from how much went into it, and that tells me my stroke volume. Okay, but remember, when you actually work out the cardiac output problem, then you have to start out with a heart rate, which will be said in beats per minute, and then I have to do what was my stroke volume per beat. So you can either give the volume amount in liters or milliliters, but it does have to make sense. 6 liters makes sense. 6,000 milliliters makes sense. 6,000 liters doesn't make sense. 6 milliliters doesn't make sense if you understand how much fluid a liter is. And all of us have drank out of a 2-liter, Coke bottle or something like that. So, or even a 1-liter Coke bottle. So imagine how much blood can be squeezed out of your heart per beat and per minute. So a reasonable answer would be somewhere around 6 liters per minute. And so again, in our final answer, we have to have not only a number, but we have to have a rate, which has to be in minutes, and a volume, which has to either be in liters or milliliters. Okay, our heart, even though it has this intrinsic conducting system, has ability to beat without neural stimulus. It doesn't mean it doesn't have neural stimulus. Notice that here's our autonomic nervous system, our sympathetic versus our parasympathetic. Now, sympathetic is our fight or flight. And notice that the things on the left side of the picture are representing the sympathetic portion. Now, they also exist on the right side of the picture, but on the left side of the picture, we're just highlighting the sympathetic. The right side is representing the parasympathetic, things that would slow the heart down. It also exists on the left, but we're just highlighting it in the picture on the right-hand side. So, when we look at the sympathetic side, the things that are going to speed the heart up, notice what we have is we actually have the cardiac nerve involved. And notice that the nerve endings are going to both the SA node, the AV node, and especially going to the ventricle area. Because if you have a scare or a fright, you get that adrenaline rush in here, then you will feel your heart jump. And it's because these cardiac nerve is sending these signals to those specific areas. And your heart even may race for just a little bit. Okay, now part of that would also be due to adrenaline in the blood that comes to the heart. But that initial quick surge of your heart beating really hard and fast at the beginning is due to that cardiac nerve. Now, notice that usually there was some sort of neural stimulus, like you saw something that scared you, and notice that you've got that cardioacceleratory center up there in your medulla oblongata, and it's going to send message down basically to your sympathetic ganglia, down to your spinal cord, through the sympathetic ganglia, and then the cardiac nerve is going to run out from there. Now, on your parasympathetic side, then you've actually got your vagus nerve to keep a brake on the heart. You've got the cardioinhibitory center up in your medulla oblongata that will trigger your vagus nerve, that cranial nerve, to actually keep a brake on your heart. And so this is going to be active more than this will be, because most of the time we're going to be in a rest and digest state, not in a emergency state. So parasympathetic, so you need to be familiar with, parasympathetic, vagus nerve, and the inhibitory along with sympathetic, cardiac nerve, and acceleratory